Okay, so good morning. I'm Richard Norris from Siena, and I'm going to talk to you today about submarine network service evolution. I think there might be a little bit of time at the end for questions, but if not, just come and find us outside afterwards. So I've got three parts to the presentation. First one, we're going to look at the network evolution towards high-speed Ethernet and look at some of the trends and technologies you need to have in your network to support the latest high-speed services. Then we're going to look at spectrum sharing. We'll look at the architectures, the business drivers, and then a little bit of the important part of actually how to share the spectrum. From experience, this is the hard part, so it's probably where we need to spend the most focus. And then the last part will be introducing a new service that I don't think many people here know much about. It's called GeoPass, and I'll take you through that briefly. So let's start with submarine network service and high-speed Ethernet. So I'm going to start with a little bit of a recap of how we've got to where we are today. This chart actually reminds me of the walk around the gala dinner last night, for those who were there. You know, a winding path around the cliffs with time markers of things that have happened over time. This is really kind of my journey in telecoms. I started in the early 90s, so this is kind of what I remember. I've probably forgotten a few things, but this is mostly what I remember. And looking at the key technology trends and the service drivers and how they kind of come together, and the network and the service these days are very tightly linked. So I started with cable and wireless back in the early 90s. That was really, PDH was still happening, for those who remember PDH. SDH was just coming out. One of my first roles, we were really introducing SDH. So there was a move from line systems to rings, from megabit systems to gigabit systems. At this time, there were some data services, but it was primarily voice-driven capacity. And the network wasn't particularly linked to the services. So, you know, you had voice switches, you had the E1s, then you had your transmission systems. So there wasn't really a strong correlation between network capacity and service capacity, but that certainly comes along. Moving on to the 2000s, I think this, for me, was the era of DWDM. It was obviously invented in the 90s, but really started to see wide-scale adoption in transmission networks and, of course, submarine cables in the 2000s. And really, we kind of started with the low capacity, you know, 16 by 2.5, 40 channels, 10 gig, 120, full gridless. And actually now we're going for less channels with our high baud modems. But that was kind of the journey from single channel to high capacity WDM systems. Obviously, the increase of speed was tremendous. We went from one channel to 120. For me, this is where we start to see the correlation between Ethernet services and transmission wavelengths. So 1 gigabit Ethernet and then 10 gigabit Ethernet. So 10 gig as a service, 10 gig as a network line speed or a channel on your WDM system. So this is the start of the correlation between what we need to do on the transmission side and what the services are actually being supported. Into 2010s, I think really coherent was the big evolution or a revolution almost in telecoms. Certainly changed things a lot for submarine cables. So we went from the 10 gig systems on-off keyed to coherent 100 gigs pretty much straight away. So we had a 10 times capacity increase, obviously growing over the 2000s, 2010s up to about 400 gig anywhere. And we saw on the Ethernet service side, we went from 10 gig to 100 gig and then 400 gig. So having line speeds that match those service speeds are really important. In the 20s, obviously we're not that far through the 20s yet, but what we are seeing, I think what I've called this is approaching the Shannon limit, because that's kind of where we've got to on our transmission technologies. You know, we're getting closer and closer with every generation of modem, and we're not going to see the 10 times capacity increases that we have seen in the past. You know, it's all about eking out the small increases for every generation these days. 400 gig E has become the latest standard that we are supporting on our networks. And certainly for submarine systems, 400 gig everywhere is the driver. So transoceanic, transatlantic, Pacific, interregion, 400 gig everywhere is what we're doing today. I think here as well, we start to see a change in the design of the wet plant. So previously there was the transmission capacity kind of followed a little bit, but now I think really the transmission technology is dictating the design of the wet plant. We've stopped chasing the very high capacity single fiber pairs. I think the Maria cable was probably the last of that generation. And SDM, or spatial division multiplexing, or high fiber count systems, that's the latest version of wet plant design, where we split the electrical power over more fiber pairs and go wider, slightly slower per fiber pair, but actually more capacity per cable. So that's the latest driver. And then, of course, sustainability. So a lot of talk in the industry, a lot of metrics being introduced, a lot of work being done to make our networks greener. So space and power efficiency are really key here. So that's my kind of quick journey over my time in telecoms and what we've gone to today. And I think the key takeaways for myself certainly is there is a very strong correlation now between line rate on our transmission systems and service rates. And it's almost one service per line. So the next thing to do, of course, is look at what's coming next. What are the next Ethernet standardizations, and how does that affect the considerations for our submarine cable systems? Just a quick recap. So I said that 400 gig E was pretty much what we're doing everywhere. This is a snapshot of some of the press releases that CN have had over the last year or so. Omantel obviously mentioned here, and quite a few others, but I think this kind of shows how the fifth generation coherent modems, WaveLogic 5 in our case, running at 400 gig everywhere, and the line rate will go higher than that, but there aren't many submarine cables short enough to support it. But 400 gig on transoceanic distances for 400 gig Ethernet services. And this is just a kind of snapshot of some of the customers that we have. This is a view of the Ethernet standardization. So going back in time over the 90s, 2000s, 2010s, this kind of matches the chart I put up earlier. And we can see that we've kind of got up to about 400 gig Ethernet today. But really, this is what is going to drive our future services. This is the roadmap we need to follow when we think about our network designs, our technologies, and how we get the highest speed services. So you can clearly see the standardization work at the moment is looking at 800 gig Ethernet, 1.6 terabit Ethernet. So that is our clear roadmap of where we need to be with our technologies. And we need to develop the fundamental transmission systems and submarine cables that will support this kind of service speeds. Why do we do that? I think it should be fairly obvious for anyone in the industry. The top part here is really showing you the drivers for what is creating these bandwidth needs. 5G, AI, the whole raft of these different service platforms that are really ramping up the amount of bandwidth we need on our systems. If you follow the work that telegeography do at most of the conferences, there's usually the hockey stick chart that talks about bandwidth increasing at huge amounts every year. So there is definitely demand for the bandwidth. Why do we go faster and faster as a single service? Well, it's about efficiency. So, if you think of 2 400 gigs versus 1 800, you've got twice the amount of cross connects, twice the amount of plugs, ports, router ports, all these things. So to have the most efficient in terms of cost, space, and power solutions, the highest possible line and client rates are the driver here. So I can see 800 gig being quite a big thing, probably adopted by the hyperscalers first, but it will percolate through the rest of the industry. And in 10 years' time, I think we'll be talking about 800 gig being the standard and 1.6 and maybe even higher being the new next requirements. So how do we do 800 gig everywhere? Well, of course, we have an answer for that, and it is called WaveLogic 6. So this is our new 6th generation coherent modem. It comes out the middle of next year. There are rumors out there that other people are perhaps suggesting it might be late. It is not late. The chips are in Ottawa. We have a lot of the analog development completed. Testing is underway. It will be in networks the middle of 24. We have orders on books already. What WaveLogic 6 does really, I've got 3 key points here. We're using the latest 3nm CMOS technology. And the reason to do that, it's about performance and it's about power. So if you looked at the anatomy of a submarine cable system, including the wet plant, the dry plant, the gateways, the SRTs, the whole thing, a lot of the power comes from these modems. So if we can reduce the power utilization, increase the gigs per watt or decrease the watts per bit, then we're going to take out a lot of power for the whole ecosystem. So 3nm CMOS is what Apple are shipping today in iPhone 15s, and it's what we'll have in our product next year. More gates on the actual chip, so we can do a lot more things in DSP and really kind of come across some of the, or compensate for some of the issues that we currently see in these systems. We can also do very high gigabaud. So gigabaud, for anyone who doesn't know, is the kind of the clocking rate of the modulation. Previously, with a 5th generation, we're at 95 gigabaud. With our 6, we're going to go up to 200. So doubling or more than doubling the actual clocking rate. And that, of course, has the impact of more than doubling the line rate. So 1.6 terabits per wavelength on short distances. But the key thing is for submarine cables, it's 800 gig everywhere. So pretty much every submarine cable that we know today will support 800 gig. And of course, more spectral efficiency. So we're not quite in the days of 10 times capacity increases, but there will be a significant spectral efficiency increase as well. So this is just a quick example of another important part on how to maximize the efficiency of our cables. So the graph here is showing performance versus channel width. And we've got a certain amount of performance or SNR, signal to noise ratio. Our driver is to maximize the number of 400 gigs we can put across this channel. So the first step is to figure out how many we can put versus that performance. We obviously have to have some margin on top, so required margin, end of life, aging, and so on. What we don't want is excess margin, the gray box. Previously, we didn't have the tool set to get around this, so it was always accepted that there was going to be a bit of excess margin, and we just kind of lived with it. We don't have to live with it anymore. With the tunability we have, these new modems, we can reduce the baud that squeezes the channel width. The modulation has to work a bit harder. We burn off that excess margin, and we make our systems more efficient. As you can see, the channel spacing reduced, so therefore we can get more channels on the fiber pair. So baud tuning is a really good new tool we have available to maximize the efficiency of our systems. Why 800 gig everywhere? Well, if we looked at what's coming on the market next year, you've kind of got 2 choices. You've got Ciena's WaveLogic 6, and then most of the vendors are standardizing on the Acacia Janu chip, which is a 1.2, 140 gigabaud system, 5nm CMOS. So if your driver was to have 800 gigs, obviously if you get a 1.6 terabit modem, you can do 2 of them. If it's a 1.2 terabit modem, you can do 1.5 of them. So more efficient in terms of how many 800 gigs you can do. And because it's a higher baud, higher capacity modem, you need less of them on the system. So you're fewer modems, fewer space, less power. So really, I think the message is that the highest baud you can get is going to give you the most efficient solutions. So we would obviously recommend WaveLogic 6, but other people have other ideas, I'm sure. So looking at now 800 gig as a service, if our demand is how many 800 gigs can I get across my submarine system? We've still got the same chart, available performance versus channel width. So 800 gig, bigger bandwidth, bigger container and so on. Still the required margin on top of it. Quite a bit of excess margin in this example. Of course, we could put lower speed services in that grey box, but if the requirement is just single channel 800 gig, again, board tuning is our friend. We squeeze the board, we drive the modulation harder, we burn off the excess margin. In this case, we reduce the channel width quite a bit, and therefore we have a more efficient system with probably more channels there. So board tuning is a really nice lever we have to pull when we're thinking about these 6th generation coherent systems. So key takeaways from the first part. We're obviously seeing a huge demand in service speeds. We've seen the alignment between transmission wavelength speeds and service speeds. We know that 800 gig is coming, so obviously we need to make sure our networks are supporting 800 gig wavelengths across the network. Higher order modems, high baud, full tunability, maximum efficiency is what our drivers should be. Okay, so that was the first part. Now moving on to spectrum sharing. So this is 3 parts to this. We're going to look at the kind of the technology and the drivers behind it, the architectures, and then I think the key question is, how do we actually split the spectrum? You know, it's very easy to say, we're going to kind of put it somewhere in the middle and have a demarcation in terahertz, but most people want to know about the bandwidth. What capacity can I get on my system? So how do we split the spectrum on equal capacities? That's where it gets a little harder. So traditionally, we had these kind of services. You had a sub wavelength, like an Ethernet service. You had an individual wavelength, like 400 gig, or you had a dark fiber. There's quite a big shift between having a wavelength service and a dark fiber in terms of cost and complexity and the kind of things you need to do to equip a dark fiber. So the middle ground really between wavelength and dark fiber is spectrum sharing. Spectrum sharing, another way to think of it, is a virtual fiber pair. So we take the available spectrum on a single fiber pair, probably about 4.5 terahertz, and we give a number of customers chunks of that spectrum that they control, and they can turn up and operate as a virtual fiber pair. So much more flexible. This is a Omdia study on who's using what in networks today. So we've got telcos, hyperscalers, and others. Hyperscalers, no surprise, they're just buying everything they can. So green means they are buying whatever they can get in the market. The interesting one, I think, is telcos. So telcos use wavelength services a lot. They use some dark fibers, but you can see on the spectrum sharing, there's a big blue box there. That means most telcos are really strongly considering buying and using spectrum sharing. So for me, this is the proof point that we need to have these capabilities in our networks. Our customers want it. We need to provide it. And of course, on the other operators, quite a significant size in the blue box there of wanting to buy spectrum services. So the demand is definitely there. So let's look at the benefits of having it for if you are a cable owner or a fiber pair owner. Really, it's about having a new service, something you can differentiate with, new revenue streams. And if you have leftover capacity on your cables that you're not monetizing, then selling it as spectrum is a nice way to do it. If you're buying spectrum, it gives you that virtual fiber pair. So the ability to choose your own SOTE, to turn it up, control it, manage it, move channels around, upgrade it, full independence of what you want to do on your service without having to go back to your network provider and say, I'd like more capacity, please. Let's wait 3 weeks while it gets turned up. You're fully independent. In terms of architectures, so the simplest one, of course, is CLS to CLS, cable landing station. We do see some people doing spectrum sharing between CLSs, probably not everywhere. If you were to go to an open cable gateway from the wet plant providers, this is kind of what you would get. But I think most people want to extend their services and have spectrum demarcation where the service demarcation platforms are. So in the POP or the data center. So having a spectrum service that includes the backhaul is probably what we'd see a lot more of. It doesn't have to be cable station to cable station. It's POP to POP is the new architecture really. course, it doesn't have to be one pop to one pop. Terrestrial networks, once you get to the cable landing station, tend to branch out to different sites. So having the ability to have multiple spectrum sharing services all across the same submarine fiber pair, but going out to different pops. And this is just basically using ROADMs to move light around, so it's pretty simple to do. Of course, the complexities are all about how you manage that light and how you load it correctly and how you fault it and so on. But this is the kind of architectures we expect to see in operators' networks, with spectrum sharing being provided at a number of POPs or data centers, all hubbing in and going across the same submarine cable system. The key thing I think here is you are getting that managed virtual fiber. So as a purchaser of spectrum, you don't have to worry about faulting and setting up the terrestrial network. That's been done by your service provider. So the network operator, the fiber pair owner, they are doing all of the photonic heavy lifting to make sure that the services are actually running as they should do. And then the purchaser of the spectrum is just taking their services at the endpoints, and everything in between is fully managed and done for them. So simplifying their operational side. I'm showing a single span originally here, but spectrum sharing pop to pop can be tens, hundreds, maybe even thousands of kilometers away from the cable landing station. It's not just a single span extension. It can be concatenated submarine cables and terrestrial. As long as you've got the available performance, it can be anywhere essentially. So if you have multiple spans, you add ILAs. If you have high loss spans, you can add Raman. If you don't need to drop at the cable landing station, you take away the more complex ROADMs and you just have an amplifier there. So decosting, simplifying the network. If you have, as we usually find, the terrestrial fibers tend to get cut more often than submarine cables, protection in the terrestrial backhaul is possible. Fast protection switching. It could be between the POP and the CLS. It could start partially the way down the system. And it could even have multiple routes. There are parts of the world, unfortunately, that have higher numbers of fiber cuts than others. So having 3-route fast switching, kind of a 1+1+1 arrangement. We are certainly doing this today, and this is a strong requirement in some geographies. So spectrum sharing is an architecture. I think it's really around the flexibility to go anywhere to anywhere as a spectrum service. It's not just CLS to CLS anymore. And I think, submarine is driving spectrum sharing, but it will be adopted in terrestrial networks. And I think it has a play everywhere, pretty much. Now we get on to the question of how do we split our spectrum? I think this is the part of spectrum sharing for me that we need to do the most work. There is still the most to do. I think the technology side of how you do spectrum sharing, the architecture, that's the easy bit. It all comes down to how you actually split the spectrum between the people buying it. And of course, this is where the money side comes in. So it's probably more focus. So when you're working with a wet plant provider and you're looking at your open cable, you haven't got the cable built yet, you haven't characterized it, you will get one performance metric, the performance versus frequency, which is a one number like this. So it's a flat performance until you've actually characterized the cable. It might be OSNR, GSNR, there's a number of different metrics, but it's one number. So the only thing you can do until you've characterized your cable is say that, okay, if I've got 2 customers that want 50% of the spectrum, I'm going to pick a midpoint. Someone gets the blue side, someone gets the red side. In the example here, about a 4.5 terahertz wide system, so 2.25 each. Ideally, this is the endpoint. We're going to split the spectrum. Someone gets blue, someone gets red. We're happy. Midpoint is that mid-frequency split. In my experience, no one wants to stop here. If they did, our lives would be a lot easier. They don't. They want to say, well, how much capacity do I get from that part of the spectrum? And this is where it gets more complicated. So the first thing we need to do is characterize the system to work out how tilted is the system? How much deviation do you have performance versus frequency? Because they're never flat. When you're buying an open cable, your wet plant vendor will characterize a certain number of fiber pairs and DLSs, but that will be CLS to CLS. If you're doing what we call a geomesh service that goes pop to pop, you need to do it with your SLTs. Most people in the industry are doing what we call a spectrum sweep. So essentially, we use our modems, we connect them onto the line, we use some software automation, we characterize the spectrum, and then we move our channels across, and we just sweep across the whole spectrum. And then we get a very clear picture of performance versus frequency. A flat transmission profile is preferred here. It makes our lives a lot easier to determine the performance of the wet plant if you use a flat transmission profile. I have seen other people talking about equalized receive profiles, but you have to kind of then unpick what's been done. So recommendation is always a flat transmit profile. So once you've gone off and you've characterized, you're going to get some different shape. For presentation ease, I've gone with the straight line. Cables are never straight. There's always some kind of deviation across. The trend is always the red side of the spectrum, which is the lower frequency, higher wavelengths, is going to be better. And the other trend is, on an average, it's going to be slightly higher than the commissioning SNR. How much higher is why you want to go and characterize it. So with this example, we're going to split the spectrum. We're going to do it on hertz still. We're going to say 2.25 terahertz each. And as soon as you see this, everyone says, oh, well, I'd like the red, please. Who wants the blue when it's going to give you less performance? You could say, well, okay, let's agree. We're going to split it in the middle on terahertz, and we're going to fix it with commercials. That's fine. Again, experience shows people don't necessarily want to stop here. They want to say, well, can we try and split it on gigabits, please? So the next thing we can do is try to introduce channel plan. And we can say, well, we're going to put channels on here. We're going to figure out how much capacity we can get across our system with our current generation of modems. And we'll create this channel plan and we'll split the capacity based on channels. This picture is for illustration purposes only. Don't try to think it's a real system. There's always a lot more complex steering wheel systems than I'm showing here. There's probably less deviation of capacities and there's less excess margin, but for illustration purposes, this is a nice, easy way to explain it. So you can see on this example, if we are splitting on terahertz still, 50% of the spectrum leads to quite a big difference in gigabits. So again, red is going to be quite a lot better. You could, of course, just say, well, that's fine. I'll just pay more for the red side. But usually people say, well, let's try to find a different split point where I'm going to get equal amounts of gigabits. So we can just say, well, we'll shift a few channels across. We'll move some channels into blue, and you're going to get something that looks like this. Because you're using channels and they have a certain width to them, it's very hard to pick a perfect 50-50 midpoint or whatever the split ratio you're trying to achieve is. So there is always going to be some kind of rounding either side of the channels. In this example, we've moved across a little bit into the red. We can't get a perfect 50-50, so we're getting 51-49, and you can see the 51 takes quite a big more of the spectrum because it's running at a lower speed. The key thing to point out, I guess, here is all those gaps. This is excess margin. Now, we could use board tuning to get rid of that margin, and we would do in real life, of course, but for the illustration purposes, I've kept it in there. That yellow triangles are something we don't want left on our system. So how do we work out how to split our spectrum with a better method? And Suboptic has an answer for us. So anyone that was at Bangkok earlier this year, the Open Cables Working Group had a paper on how to change or move your GSNR performance into capacity, and then how to split the spectrum based on that capacity. So Going back to our friend Claude Shannon and his equation on how to get capacity across a system. So GSNR, performance of the wet plant, converted into spectral efficiency. The key thing about this one is what we're doing is we're slicing that performance profile into thousands of different, very, very tiny slices, probably like 1 gigahertz, so gigahertz wide each, working out the Shannon capacity of every slice. And then we have a lot more ability to split the spectrum based on Shannon capacity. Shannon capacity is the perfect modem. There are no channelization or gap to Shannon things in there. There is no excess margin. So this gives you a real perfect view of what that cable is able to perform to. So this is where we've started to go with our customers recently, working out the Shannon capacity of a cable, then how to split the spectrum based on equal numbers of Shannon capacity. So if we go back to our example, we use the Shannon method, we slice it up, we get a perfect 50-50 capacity, and then we can say the demarcation point in terms of hertz or terahertz to get equal capacity is exactly there. So this is the process that I've personally gone through a few times with customers this year. Suboptic, the paper that was put out there is pretty good. I think a lot of people are starting to use it. In terms of further reading, a couple of documents here that or places to get more information. We've written a spectrum sharing handbook, which is available to download, free download on Ciena.com. Suboptic, following on from the Open Cables Working Group, now has a spectrum sharing working group. I have got the honor to run that group. Really pleased to see a few people from the conference here. I know Amantel have joined recently and have a representative there. But we're always open to more input. So if you want to join the spectrum sharing working group, go on to suboptic.org and please register your interest. So spectrum sharing, key takeaways. Until you've characterized the cable, you're just guessing on how it might perform. Not good. So first stage, characterize the cable, work out what the performance looks like. You can use real transponders, but there's going to be some imperfections there and some excess margin. So the recommended method to get a really clear view of the capacity split is to use the Shannon method and following the suboptic guidelines. Okay, so that was spectrum sharing. Now for something different, GeoPass. I should say this is a name that I came up with. My marketing department don't particularly like it, so it might get renamed at some point, but they haven't told me what to rename it, so this is what it is. What is it? I think the simplest way to say, and this is the driver behind it, was how do we do a airline alliance model with telecoms? So Star Alliance, One World, whoever your preference is, whoever you want to get your air miles from, how do we do the same model with telecoms? The name GeoPass, geo is obviously geographic, AAS as a service. What marketing don't like, the P, I think there is a platform as a service is an industry recognized term already, so they didn't like that. It could be photonics, because that's essentially what it is. I think a key theme from this conference I have heard is partnership. So I like this as partnership as a service, because that's really what this is all about. My example of flying here today is not, or yesterday, was not quite accurate because Amantel is not quite part of One World yet. But in theory, this is about how you go to your home provider. You want to have a service that goes beyond their reach. They use their partners through their alliance to extend their service capabilities. And you have one contract, one billing, one set of billing you have to pay, one money. And then if you have any issues with your service, you've got one contact point. So rather than having to buy lots of bits of network and stitch it together yourself, you're using your service provider and their partnerships to give you an end-to-end reach. Good example of how it might work. So two operators, one operator's got a transatlantic system, the other operator's got a Europe to West Africa system. their networks come together at a common point, and they are joining their GeoPass partnership to have services that could be due. So if the US entity for the transatlantic cable could sell a service from New York to Lagos, a South African entity could sell Cape Town to New York, and the key thing here is they have control over the end-to-end service. They're not handing off some system, some spreadsheet to their partner and saying, please do that for me. They've got full control over provisioning, performance monitoring, billing data for the end-to-end service, which is the key thing here. How do we do it? Well, it comes down to just basically interconnecting networks and then having a shared service layer. So two simple network views here, operator 1, operator 2. Each one has their networks with their submarine cables, their terrestrial backhauls, all the photonic components, terminals, ROADMs, amplifiers, and so on. But across these two networks, there is a thin shared service layer that they can both manage. And that's the key to this one. To view it in terms of equipment, so you've got the ROADMs and terminals of each network operator, and you have a thin layer of transponders that are being shared between both operators. And both operator can access their transponders, they can turn up services, they can get the PM data, they can do the performance monitoring. Obviously, there has to be some agreement on time slot usage and naming conventions and troubleshooting and so on, but that's not particularly difficult to do. And how we're doing that? Well, it really comes down to just using the management systems that are there. We could attack this with software-defined networking. We could have lots of APIs and complexity and development and cost, but we don't need to. To do this today with the systems that people have in their networks, you basically have a network management system for each operator. They control their photonic networks. And then you have a shared management system for the shared service layer, which both operator has access to. So if operator 1 wants to turn up an Ethernet service over that shared transport layer, they have access through their management system. They click the endpoints, turn up the service, hand it off to their customer. So it's really a fairly simple way to achieve something that could be quite complex, but really doesn't need to be. So in summary, I think a new partnership solution to extend the reach of people's networks, to maintain their single point of customer contact, but have a lot more potential reach. I'm showing 2 networks here as an example. 2 is not the ideal number, probably a lot more than that. You look at the airline alliances, maybe 10 different operators is the model. This is fairly early days. We have to pick a proper name that's marketing approved. We have done some proof of concepts. We are going to do some field trials later this year. But if you're interested, please come and talk to us. And with that, I think I'm done. So do we have time for questions? Are there any questions?